Okay, yeah. So, hello everyone. Thanks for coming, and I guess welcome back to this new year of talks. So, I just want to say before we start that last year we had a whole host of exciting talks by a bunch of great people, some of whom are also here today, and most of them, if not all of them, can be found on our YouTube channel as well as linked on the accompanying Discord server. And I also want to say that this year we've already got a pretty great lineup of speakers to kick off the fall semester. So we've already got talks in mathematics, including the one today, high energy physics and condensed matter physics already kind of lined up for everyone. And yeah, so we're really excited to start off this new year of speakers with our resident bird enthusiast and MIT math student, Cameron Krulewski. And she'll be speaking to us about her upcoming work on free to interacting maps and the Bott spiral. So whenever you're ready, you can take it away, Cam.
Okay, thanks so much for the invite and the introduction, and thanks everyone for coming. Let me try to share screen. Okay. Okay, let's go to Notability. Okay, so I'll be talking about free to interacting maps and the Bott spiral, and this is joint upcoming work with Arun, Natalia, and Luke, who are all on this call, I believe. So glad that they could all make it, and I hope I'll do justice to our joint project. So first of all, a little bit of introduction, just to remind of the general idea of SPT phases, or symmetry-protected topological phases. So usually we think of a phase or a quantum phase as being given by, well, we start with some, let me move this down. So we start with some moduli space of models, often in terms of maybe Hamiltonians. And then we'd like to maybe remove some critical locus, so some critical behavior. And then we'd like to take the connected components of this kind of space, and we'd say that a phase is a connected component living here. So for SPT phases, okay, but the thing I want to emphasize is that sort of implicit, either when I define what my moduli space should be, or when I define what I mean by the connected components, is the choice of sort of allowed deformations between equivalent models. And these allowed deformations will determine which, how many connected components I have. So for SPT phases, any deformations have to be symmetry preserving. And I can decide at the beginning what symmetry that should be. So for example, I could have a given model and it might possess several symmetries, and then its phase as a SPT phase would depend on some choices I make. But usually there's not too many interesting choices you can make. And what's special about symmetry-protected topological phases is that usually you say that when you relax this condition, so when the deformations preserve symmetry, you get some non-trivial component, but when you allow the deformations to be something more general, you end up landing in the trivial component. And it's not all, there's a little subtlety about what it means to be in the trivial component, but for at least today, or when we're talking about Hamiltonian models, the trivial phase should be connected to a model whose ground state is a product state. Ground state. Okay. So it's been a long-standing question for symmetry-protected topological phases about whether they're robust under interactions. So what does this mean? I could write down a model that's free in the sense that it doesn't have really high order interactions between particles on different lattice sites, and we'll see an explicit example a little bit later. But people have studied many different examples of this for different kinds of symmetries, for different setups, and it's an interesting question when I change my deformations from being free, so usually let's say in the context of fermionic systems, this will be deformations in the form of two-body. Let me just say two-body interactions in general. Or more general interactions. So this could be higher order. So when I say a free to interacting map, what I want is a mathematical map that I'm going to write as F2I that takes the class of a model considered with free deformations and a connected component here to the same equivalence class of that model, but now considered under a different set of allowed deformations. And I'll scroll down. So today, for these fermionic systems with certain symmetry types, we're going to model these free theories as living in a K-theory group. So many of us are probably familiar with the tenfold way of free fermions, where we have the dimension of the system coming into play. We have another parameter, which I'm writing as S for now, that depends on the choice of symmetry. And there may be a normalization there. And so what I want is some kind of map to interacting phases. And I like to model interacting phases as invertible field theories. Or today, they'll be modeled by Anderson dual bordism groups. And I'll say more about the bordism groups a little bit later and explain a little bit more about what these decorations mean. But this just has to do with the symmetry type of the theory. So these are the kind of maps I want to introduce today. But then I also have a specific application in mind. I'm not going to talk about them in the greatest generality. So we wanted to apply them to study the phenomenon called the Bott spiral, which appears in a paper by Queiroz-Khalaf and Stern. And the way they studied this question of free to interacting theories, but they did it by using an approach of dimensional reduction. So they would start with one free theory, they'd dimensionally reduce to get a theory in one dimension lower with a slightly different kind of symmetry. And then they would look at the interactions. And they found this really large, they found this increasingly large two-torsion classification for the interacting phases if they started with a Z classification. So let me start filling in sort of the suggestions of a commutative diagram here. And I'll be a little more specific on these parameters later. But so here will be some free to interacting map. Here is what is the modeling the dimensional reduction map of Queiroz-Khalaf-Stern. And one thing that we did was we extended their dimensional reduction map to the interacting side as well to study what was happening there. And so we'll start off over here with appropriate parameters. This will be a Z class. Queiroz-Khalaf-Stern kind of traced it around. They dimensionally reduced, and they got some big Z mod 2 to the n, or this is at least a subgroup of the classification over here. So for increasingly large n depending on the dimension d. So that was a phenomenon we wanted to understand using free to interacting maps and using some other things we understood about symmetry breaking. So let me dive into the left side of this diagram, or at least the top, or at least these two K-theory groups, and let me recall the tenfold way. So for free fermions. So probably the statement is familiar to most of us. So free fermion, SPTs, in dimension D, with some kind of symmetry parameter S, is going to be given by this K-theory group, which I already wrote above. I wanted to insert a picture here, which is slightly modified from Queiroz-Khalaf-Stern. So the reason that Kitaev's paper about this was titled The Periodic Table is that this classification features a periodicity. So sometimes people refer to this as the Bott clock. And I learned while Googling that apparently a Bott clock is also a different kind of thing. That's a particular model of a wooden clock, but I think no relation. So this is not only aperiodic when I increase the dimension by 8 or modify these symmetry parameters, but it also features a 1, 1 periodicity. So if I increased d by 1 and decreased s by 1, then I would have the same classification. So in particular, if I had some model in class BD1, such as the time reversal symmetric Majorana chain, this has a Z classification, and it's the same classification appears for a 2D class D superconductor. So class D means no additional symmetry. This is also classified by a Z. So I can imagine using this 1, 1 periodicity. And the reason I'm belaboring this point is that it's not going to be true once we go to the interacting side. So to use a framework that will be useful for both the free and interacting discussion, I'll define fermionic groups. So I think these are studied by Benson and Stoltz, and I learned them from Luke, who is on this call. So the data of a fermionic group is going to encode the symmetry of our system. So the data includes a topological group, G sub B, and here B stands for bosonic. It includes the data of an extension by fermion parity. So that's going to be an extension of this form. We'll call the middle group G sub F. And this extension corresponds to a degree 2 cohomology class in the cohomology of BGB, C2 coefficients. And the last piece of data for this fermionic group is going to be a grading. So a grading on GF, so a map, I'll call it theta, mapped from GF to Z mod 2. We're not going to decorate this Z mod 2 with a T, because what this grading is supposed to encode is whether the symmetry generators in G sub F are unitary or anti-unitary. So labeling, let's see, time reversing, which would be anti-unitary, or preserving elements of our symmetry generators. And similarly, this grading, I can abuse notation a little bit. So similarly, this grading gives me a degree 1 cohomology class with C2 coefficients in the cohomology of BGB. And so with this data of the symmetry, knowing how it interacts with fermion parity and knowing which generators are time reversing, time preserving, I can form this into an algebra, which I will then take the K-theory of, a slight modification, and get my classification of phases. So from this data, I can define the fermionic group algebra, which I'll denote as RF of all of this data, GB theta omega. This is going to be the group algebra on GF, but where I mod out by one constraint, where I'm going to identify fermion parity with -1. So I will now do a couple examples of this, and for today, we're really just going to focus on internal Z2 symmetries, because this is what is relevant for our application. And so to set some notation, I'm going to write the cohomology of BZ2 as being generated by X. So X is the name of my generator. Okay, so let's do some examples right away to make things concrete. So one kind of symmetry you might be interested in is a class BD1 system. So this has a Z2 time reversal symmetry, such that this squares to 1. So since the bosonic, the underlying bosonic group is just going to be encoding that single symmetry generator, then because T is the time reversal, it's an anti-unitary symmetry, we're going to choose the non-trivial theta. So we're going to choose theta to be the identity from Z2 to Z2, or correspond to the cohomology class X. And since we want T squared to equal 1, we're going to need the trivial extension by fermion parity. So I'm going to take their product in the middle here. So this is our bosonic group. So I take the Z mod 2 to cross Z mod 2 instead of the Z mod 4, because if I had Z mod 4, this subgroup inside, I would have T squared, giving me fermion parity instead of T squaring to 1. So I make this choice, and this middle group has a name as a fermionic group. This corresponds to pin 1 plus. So just recalling the spin group and the pin group with pin plus or pin minus signature, they all live inside the Clifford algebra. And so this corresponds to pin plus. And I can compute, for this example, the fermionic group algebra. So I first take the group algebra on this group, but then I'm immediately gonna, mod out by fermion parity, so that's going to kill this factor. And what I'm left with is the generator. I'll write it as A, but the generator coming from time reversal. And I said that time reversal squares to 1, so I'm gonna mod out by E squared is 1. And so there's another name for this algebra, namely the Clifford algebra on 1 positive generator. So let me make one note and then I'll do a very related example. So note that this choice of twist for theta and omega encoding my symmetry corresponded to this generator of the cohomology and then a 0. This corresponds to a vector bundle, specifically the tautological bundle, sigma over BZ2. And I'll come back to this idea. So the related example I want to do is just the other case of time reversal. So this would be class D3. I have a Z2 time reversal symmetry, T, such that T squared now, instead of giving me 1, will give me fermion parity. In this case, T is still anti-unitary, so I'm going to take theta again to be the identity, but now I'm going to choose the trivial extension. Sorry, the non-trivial extension. So I'll write this as Z4 and I'll label it by T and F. And this group also has a name in the middle here. This corresponds to pin 1 minus. And I see here that when I take the generator of the C mod 4 and I square it, I indeed get fermion parity. So now the fermionic group algebra, according to this fermionic group, I'll again have my generator, but I'll mod out by fermion parity squaring to, so when I take the fermionic group algebra, I need to identify fermion parity with -1. So I'm going to end up with a generator A, but now A will square to fermion parity, which has been identified with -1. And so now this algebra also has a name that we're familiar with. It's just the Clifford algebra on 1 negative degree generator. So in some sense, these will be the only examples we need. Let me also note here that this theta omega combination, these two non-trivial guys, this corresponds to 3 copies of sigma. It also corresponds to minus sigma if we choose to allow virtual bundles. Okay, so what do I do with these fermionic group algebras?
Sorry, Cameron, can I ask a question?
Sure. Yeah, for sure.
When you say corresponds to, what does that really mean when you say that?
Yeah, so I mean that this is W1. Thanks for that. Hopefully I didn't, correct me if I made a mistake, but what I mean by corresponds to is that this data of these two cohomology classes, or the data of the twist of this algebra that I'm forming. In these two cases, it comes from a vector bundle. In general, it doesn't have to. But that's what I mean there. Does that sound good?
Yeah, thank you.
Thanks for the question. That's a good, I should have mentioned that. Okay, yeah, please feel free to interrupt with questions. Sometimes I'm not looking at the screen so much, so I won't notice. Okay. So these are two very nice examples. I want to sort of immediately generalize to the situation we're going to want. So let me define EL comma K be a bunch of products. So be the fermionic group. That's a bunch of products of pin 1 minus, where I need to be careful taking the product to respect the grading and all of the data. This would correspond to the Whitney sum of vector bundles, assuming my twists come from vector bundles. And I'm going to take L copies of one, K copies of the other, and implicit in this notation is the data of all of those thetas and omegas. Then it turns out that the fermionic group algebra on this group will give me the Clifford algebra on these generators. So there's a canonical isomorphism of superalgebras. And I think knowing that the Clifford algebra was a twisted group algebra of Z mod 2 to the, so the underlying bosonic group is Z mod 2 to the L plus K. This was known for a long time, and then just framing it in this language will make it really useful for us to compute with. So how do I finally get to K theory with this data? When I have all the data of the symmetry types of my system, I'm going to feed that in, but first, let me say for a finite dimensional superalgebra. I can take an Atiyah-Bott-Shapiro type approach to the K theory. So the K theory in degree K, hopefully that's not too confusing, in degree K is going to be looking at graded modules over my algebra that extend to Clifford minus K, or A tensor Clifford minus K. These will be graded. Modulo those that extend to one more Clifford generator. And again, this will be graded. So of course there are many, many models for K theory. Often when we're looking at the K theory of a topological space, we'll think about vector bundles. If we're thinking about C-star algebras, we would consider these modules over the algebra to be acting like, there's a very nice way to see how that relates to the vector bundle picture. And so there's many ways you could come at this, but this Atiyah-Bott-Shapiro type approach will be the easiest for us today. So let me write down how we get the tenfold way from all of this data. So now, free fermion SPTs in D dimensions with, let me specify to our case of interest, so at Clifford L comma K symmetry. So where we have a bunch of Z2 symmetry generators. This is going to be given by K theory. Again, I need to sort of shift my degree by 2, but I'll plug in the C-star algebra functions on ZD. Since I'm imagining my system is in D dimensions on a cubic lattice, it would be more complicated if the lattice was a different shape. I can tensor with Clifford L comma K. And if I use Baum-Kahn or a Fourier transform, and I use the suspension isomorphism in this form of K theory, so I see this degree here is related to the degree of the Clifford algebra, I can rewrite this in the way that is maybe more familiar that we started with. So I have the K theory in degree D plus L minus K minus 2. Okay, and so
Hey, Cameron.
yeah, sure.
Can you clarify, please, what kind of transform do you use? You mentioned Baum-Kahn, you mentioned Fourier. I'm confused.
Yeah, so when I mean those to be, so I'm viewing the Baum-Kahn as a generalization of the Fourier transform, and that will rewrite the KO homology of this algebra in terms of the functions on a torus, and then I guess implicitly I'm taking the strong phase of the system, or I'm picking one cell of that torus to focus on, so maybe I should be a little bit careful, but that'll give me a d-fold suspension on the K-theory side. There might be some involutions to keep track of, so I'm suppressing some details, but is that okay?
Yeah, thank you.
Okay, yeah, thanks for the question. Yeah, and then on this side, I'm using the suspension isomorphism. Okay. So great, I just wanted to observe here that the form of Bott periodicity that comes in at this point is that the Morita class, or the category, the equivalence of the category of representations of this algebra, or of Clifford L, K, depends only on L minus K. Okay. So let's see. Let me go ahead and, right, yeah, so let me go ahead and do an example quickly. So I want to, I forget what number we're on. I think we're probably on 2. So what happens when we change our system to consider interactions? So let me go back to an example. So class BD1, and let me choose the term reversal symmetric Majorana chain, just because I really like this example. And this was studied by Krulewski-Kitaev, and this is one of the first examples of a system that had a different classification for free and interacting. In this example, we have some sites in a 1D lattice, but I'm going to draw them as blobs. And on each of these sites, I'm going to have the creation and annihilation operators acting on a C2. But what I'd like to do is make a change of basis so that associated to each site, I have 2 Majorana operators. And I won't draw the rest of those, but the just to be explicit, the basis transformation the change of basis we're doing is the following, where the odd ones are a difference of the creation, or the sum of creation and annihilation operators, and the even ones are the difference adjusted by I. So this model has a time reversal symmetry, but let me write down the 2 possible phases this model could be in. So one phase could be where I write down a Hamiltonian. I'm going to adjust it by some factor here, where I pair these modes on the same site. So what the picture people usually draw is the following. So I connect all of the modes that are interacting with each other. And in this situation, the modes pair up and sort of form one fermion on each site, which is what we started with. We sort of broke them up into half a fermion. And you can solve this model and you can find that it has a product ground state, which is why I'm allowed to call it a trivial Hamiltonian. Now, the non-trivial model on similar data is going to make the opposite choice of pairing. So now I'm going to pair Majoranas between sites. Yeah, I'm hoping that this model is somewhat familiar, which is why I'm going a little bit fast through it, but if something doesn't make sense, please stop me. So the way I would draw this is I'd pair model the fermions between sites. And if you solve for the ground state of this model, it would not be trivial. If I sort of wrapped around on a circle, I would see that this corresponds to the Mobius bundle. And on a finite wire, I could find that there are some interesting Majorana edge modes going on here. So this phase is non-trivial, and it turns out or Fitkowski and Gatayev showed that I can stack systems. What it means, so I can stack copies of this. Stacking means I tensor the Hilbert spaces my model is acting on, and I add the Hamiltonians where I tensor with the identity where necessary. But if I stack a whole bunch of copies of this Majorana chain, and I only allow free symmetry-preserving interactions, I can never relate it to the trivial Hamiltonian or any number of copies of the trivial Hamiltonian. And from this physical observation, I want to say that the class of this model generates the relevant K-theory group. So the K-theory group was in dimension 1 with one additional symmetry, so the time reversal symmetry, and the signature ends up being a plus, and I correct by 2. So in KO0, which as we kind of saw earlier was a Z classification. So I can stack as many of these as I want, and I can't trivialize it using fermion bilinear terms. However, Fitkowski and Gatayev did a lot of work, and they showed that. So Fitkowski and Gatayev showed there exists a term, actually a quartic term, that does trivialize after we get to 8 copies of the Majorana chain. So I won't write down the term for you because it's a little complicated, but they found this term. And so the physics conclusion is that if we view the free interacting map as taking the class of this model under free fermion two-body interactions, I should say, and then we consider it instead to be an interacting model, the classification breaks down. And this map is actually a mod 8. And yeah, one other thing I should add is that this paper of Queiroz-Khalaf-Stern that I'd like to talk about, they showed that quartic terms will actually suffice for any of the tenfold way examples. But what I would like to do now is recover this phenomenon that you can view from the lattice model using bordism and TQFTs, so using low energy field theories. So let's keep this example in mind, and we'll try to get back to it. So I think I'm on 3, so bordism and TQFTs to understand interacting phases. So I said before that fermionic groups are going to be really helpful for thinking about both the free and the interacting classifications at the same time. And the reason that is that when I have a fermionic group, I can also get a tangential structure on some manifolds that I'm considering. So how I build this explicitly, I'm going to scroll down. How I build this explicitly is, so the data of this fermionic group, these theta and omega, gave me a map to BZ2 cross B squared Z2. So the classifying spaces for H1 and H2. So theta and omega gave me this kind of map. To get a tangential structure on a manifold, I'd like to have a map to the orthogonal group that tells me what structures I need to preserve. And so how does all this information come together? Well, I'm going to take the first Stiefel-Whitney class, and I want to say that I'm just going to take the second Stiefel-Whitney class. I do need to modify this a little bit to swap tangential and normal structures by adding on a W1 squared here. So now I'm going to use this data of the fermionic group to form H as the pullback. So this will be my definition of the tangential structure H. And you see it comes equipped with a map to the orthogonal group. So when I have a manifold and its tangent bundle, I can ask whether it has an H structure by asking whether the classifying map of the tangent bundle lifts through this BH. Okay. And so more precisely, one thing we actually show is that the assignment of a fermionic group equipped with the fermionic tensor product gives us a symmetric monoidal functor from fermionic groups equipped with that structure to empty spin modules, where if I map to the Madsen-Tillman spectrum of this kind of structure, MTH, I have an empty spin module, and I can say more about it if people are interested in like Madsen-Tillman spectra, but I won't immediately say anything unless someone asks me a question. So how are we going to get from lattice models and this kind of symmetry data and tangent to something where we can plug in tangential structures? To do that, we really need to go through an ansatz. So the ansatz is that if I have a lattice model, and let me say d-dimensional, and let me say for today that we're going to be interested in a free fermion lattice model, and it has some kind of symmetry that we're specifying in this way. Given a lattice model, I'm supposed to be able to take a low energy field theory. And what I expect to get out is a d+1 dimensional topological quantum field theory with H symmetry. So to take a low energy field theory, or to look at the low energy behavior of the lattice model, means that we're really focusing on its ground states. That's a perfectly fine thing to do for studying symmetry-protected topological phases, because these phases are really sort of only their ground states are interesting. And in fact, Kitaev conjectured that the sort of space of the most general SPTs you could think about should deformation retract onto the space of ground states. So it's good that we're keeping that information. Concretely, this TQFT, when I plug in a when I plug in a D-manifold, I want to assign the state space of the TQFT to that manifold. The state space I assign should be the ground state of the lattice model. And there might be a couple other desiderata we have, but I won't write it down because it depends a little bit on the form of the lattice model that we're given. So let me treat this as motivation for looking at topological quantum field theories with this kind of symmetry. And if you'll allow me to admit this ansatz and then specialize to put a few more adjectives in front of the TQFTs here, then that would be great, because then I can apply a theorem and tell you the classification. So the theorem that I want to apply is due to Fried-Hopkins, building off of work of Glacius, Madsen, Tillman, and Weiss, and Wynne, Jean-Meprise, and others. And there's also a non-topological version due to Grady. And I'm going to use the topological version today for simplicity. This theorem tells me that when I specialize to invertible TQFTs that are also unitary, which is a good physical assumption for us, they'll also be fully extended, which is a good assumption for locality purposes. So TQFTs in n dimensions with H symmetry. And let me point out that invertible in particular means that the state space they assign to any manifold you put in is going to be one-dimensional, and that is what we would expect for an SPT phase. We don't want to get multiple ground states. We're not looking at anion models here. Okay, but now these are the kinds of TQFTs that are of interest. We're going to mod out by taking the deformation class. Turns out we can identify this with a group of homomorphisms from a bordism group of manifolds with H structure to C cross. And I imagine this homomorphism is telling me the partition function of the theory of my TQFT. And these particular kinds of TQFTs are expected to be determined by their partition function. So that's sort of the reason that this is showing up on the right-hand side. Okay, so then let me recall, just in case, the definition of this bordism group. So omega h, and I'll stick with this degree. So this is going to be the group generated by closed n+1 manifolds with H structure. And I'm going to mod out by the relation of bordism. So bordism between two manifolds M and N that have an H structure is a manifold W, also with H structure that restricts to the H structure on M and N, such that the boundary of W is going to look like M on one side and N on the other. So I will get to some examples of these groups, but first let me give one more definition to kind of tie back to the fermionic groups. So I should say, in applying this theorem and using this ansatz, I want to classify the interacting theories, and the way I'm going to do that is just by computing some bordism groups, which we like to do as topologists. So the one more definition I'll give you before we look at an example is that of a twisted spin structure. I alluded to earlier that we have some relationship between fermionic groups and empty spin modules. What that really means concretely is that we can relate H structures to spin structures by some kind of twisting. So let me tell you the definition to be concrete. So let's let X be a space, and let's let V over X be a vector bundle. Then an X comma V twisted spin structure on some manifold M is the following data. So I take a map. I need to be equipped with a map to X, and then I ask for a spin structure on the tangent bundle of M plus the pullback of the bundle V. So the way I like to think about this is that we could have started the day with some spin manifold M, but turns out it's not quite spin. The way that it fails to be spin is captured exactly by this vector bundle V and the characteristic classes of that bundle. And so the way I can kind of fix M to make it spin is by adding on the pullback of that bundle V. So let's do two relevant examples to our story. So let's let me immediately give an example here. So for class BD1, recall from up here, let me scroll up. So for class BD1, we found that these characteristic classes corresponded to the tautological bundle. And I said that a little informally, but what that will mean for us here is that this group omega pin minus of n-dimensional pin minus manifolds I can identify with n manifolds that are twisted spin. So manifolds twisted over BZ2 by the bundle sigma. And hopefully I'm getting my signs correct here, but we shall see. So this is good to know, and then I can compute, for example, the classification of interacting SPTs on, so let's see, on two manifolds with pin minus structure. So I pass through the ansatz in order to say these interacting SPTs, and then I say I'm going to classify TQFTs, then I apply Fried-Hopkins. That tells me that this should be maps, homomorphisms from a bordism group pin minus degree 2 to C cross. And it turns out this bordism group pin minus is a Z mod 8, is generated by RP2. And so the Z mod 8 is precisely the Z mod 8 that Krulewski and Atiyah found for the interacting order, the order of the interacting Majorana chain. And so DeBry and Gunningham in a paper studied, one of whom is on this call, studied the Arf-Brown TQFT, which was related, which described the low energy behavior of that Majorana chain. Okay. And yeah, so you can see if you modify, if you modify the tangential structure appropriately using the bundle sigma, you will get a spin structure. I have one pin plus example, but maybe in favor of time, let me jump a little bit to the more general system, the more general setup that we're going to want. So let me recall, we had this fermionic group EL, K. This was a bunch of copies of this fermionic group pin minus, and a bunch of copies of the fermionic group pin plus, pin 1 plus. So if you like spectra, I'm going to define the following. So this will be, so I'm going to define a tangential structure that encodes this information. The way that I encode it is saying, okay, I have L many twists over BZ2 by the bundle sigma, and I'm just going to correct for the dimension there. And I have K many twists going the other direction. I'm going to choose minus sigma instead of 3 sigma. So you can read this as just saying I have a twisted spin structure where I twist by Z2 by sigma L many times and by Z2 with minus sigma K many times. The actual formula I wrote down is the formula for a Madsen-Tillman spectrum, or a smash product of several of those spectra, where I'm taking the Madsen-Tillman spectrum of, or the Thom spectrum of sigma here, and the Madsen-Tillman spectrum of minus sigma here over BZ2. Okay, so now this is a tangential structure I can study. And I wanted to return to that idea where we had this, on the free side, this Morita invariance, or this periodicity where I only saw L minus K. But now that I've turned this into a twisted spin structure, I really care about L and K. So let me consider LK to be 0, 0, 0. So this is a spin structure. Versus 1, 1. This is something called a D-pin structure in the literature. And I can already see, so in low dimensional bordism groups, I could compute. And I read this computation in a paper by Kaidi, Paramartinez, Tachikawa, and DeBry. But these low dimensional groups, these groups don't even match in low dimensions. Like, it's really a different condition I have on a spin manifold versus a D-pin manifold. So the spin bordism groups agree with K theory. And these low degrees, I get a Z, Z2, Z2, 0. And in this paper, they computed that the D-pin classification, so manifolds with D-pin structures, is already differing in degree 0, and then it continues to differ and get a Z mod 8. So to be concrete, this twisted spin condition, even if L equals K, is not the same as a spin structure. So for example, in degree 3, I could have, so let me say what the structure. So a spin structure on TM asks, is the requirement I need to define a bordism class there, versus, on the other hand, it turns out I would be asking for a spin structure on TM, but then I'm allowed to add and subtract an auxiliary bundle. That comes from looking at what this twisted spin condition means for the tautological bundle. It turns out I can modify by a sum and a difference of 2 other line bundles. And then if that's spin, then I'm allowed to be D-pin. So for example, something like RP3, I could modify it by taking a trivial bundle and taking 1 copy of the topological bundle, but on this side, RP3 is not spin. So just really explicitly showing the difference between these two these two classifications. Okay. So that's what I wanted to say about the failure of Morita invariance when we try to encode this data of this fermionic group for Z2 twists on the interacting side. But the title
Should
of my
that
talk...
be RP2 or something? I'm a
let's
little
see.
confused. RP3 is a group, so it has everything.
I could have made a mistake here, so let me think. So I definitely want it to be in degree 3 here. So sorry, was your objection that RP3 is spin, or what was... Ah, yeah, sorry. Thanks, Arun. So I just made a typo here, so let me do this. Thanks a lot for the correction. So are we happy now with this example?
Yeah,
Okay.
thanks.
Great, thanks a lot. Yeah, that was a typo there. I know I'm writing, but it was still a typo. Okay. Okay, so I want to get to free to interacting maps. I don't remember if we're on 3 or 4. I'm going to guess we're on 4. So there are a lot of ingredients that go into a free to interacting map. I'm going from some K-theory class to some TQFT, but the part of it I want to focus on today is just how would I go from K-theory to bordism, or the other way, from bordism to K-theory. And the way to do that is to use some twisted versions of the Atiyah-Bott-Shapiro orientation. So the classical version, or the untwisted version, of the Atiyah-Bott-Shapiro map is going to run from spin bordism in degree K to a shift of K-theory. And there are many, many ways to say what this map does. I'll choose to say that I take a spin manifold M to the K-theory class of the kernel of its Clifford linear Dirac operator. So this is a Clifford K linear Dirac operator. And this is acting on sections of the spinor bundle of M. And so to form this Dirac operator and make it Clifford K linear, I really need to use the spin structure on M. I need to use the spin structure to build the spinor bundle and to build this operator. And then on the right-hand side, I consider the kernel of that operator, and I remember that it has the structure of a Clifford K module because it was the Clifford K linear Dirac operator. And if I am happy with the definition of K-theory as Clifford modules, then you can see this should land in KO minus K. So that's one way to phrase the classical definition. And I just want to emphasize that we really need the spin structure to do this. So what do we do when we start with something like D pin or or pin plus or pin minus and we don't have the spin structure? Well, we have to modify what this map does. So there are some generalized Atiyah-Bott-Shapiro maps. Let me go over the ones for pin plus and minus. So these were studied by Fried and Hopkins, and they also studied the 8 other cases, 6 other non-classical cases in addition of these Atiyah-Bott-Shapiro type orientations for 10 different tangential structures. And so we'll need to bootstrap up from their constructions in order to get something that works for more general L, K twists that we would like to study. Okay, so they didn't phrase it quite in this language, but I'm going to write down the 2 maps that we could study in the following way. So if I instead start with a pin plus manifold, a pin plus manifold is a twisted spin manifold, so it's twisted by 1 minus sigma. So something that I can do is I can take this pin plus manifold, and from it I can construct a spin manifold with an extra map to Z2 by taking something called a Smith homomorphism. And I'll wait a bit to say anything about these in generality, but concretely what we do is we take a manifold M with this structure and we map it to the intersection of the 0 section of sigma with a generic section over M. So the 0 section of sigma over M just looks like a copy of M. And then we take a generic section, and differential topology will tell you that these intersect transversely, and their intersection defines for me a manifold of codimension 1. And if you are careful with the tangential structures, you can show that because we cut out by sigma, which was precisely the way that M kind of failed to be spin, we modify the tangential structure on the submanifold we cut out, and that submanifold we cut out actually is a spin manifold. Okay, so my arrows might get a bit wonky here, but from that spin manifold, we're just going to forget that extra Z2 structure. And then we can actually follow through with the classical Atiyah-Bott-Shapiro, which I'm going to label as 0, 0. And yeah, we'll land in KO n minus 1, pi duality, and I get 1 minus n. In the other case, so for pin minus instead, I can again write this as a twisted spin structure. Now I'm twisting in the other direction. And I'm going to use a class called lambda, and I'll say more about that if people have questions, but this is some K-theory class that or some map that I form using the difference bundle construction applied to sigma. So that's one sort of geometric way to say what it is. And let's return to that maybe when I get to the general case if people have questions. But again, I can get a spin manifold in a different dimension, and I can use the classical Atiyah-Bott-Shapiro. So how do we generalize this for our case of interest, which is these more general L, K twists? Well, I want to define some ABS map for L, K. And I want it to start from some manifolds that have a twisted spin structure. So I'm writing this in terms of spectra, but recall that this just meant this EL, K was the same thing as twisting by some Z2s. So BZ2 sigma minus 1, L many copies, and then BZ2 1 minus sigma, K many copies. So this is my starting point, manifolds with this kind of structure, and I need to get down to K-theory using sort of the ingredients from the previous discussion. So something I can do is I can take the classical ABS map on this first factor, I'll land in K-theory. I can then smash it with this class I called lambda on the previous page, and I'll do that L times. And that'll land me in K-theory, but shifted by 1. And I'll get L many copies of that. And then on these last K factors, I can use the map of spectra inducing the Smith homomorphism, or I guess, to be careful, a suspension thereof. And this will get me to, this will actually just get me to BZ2 plus, if you don't like spectra, don't worry about the details here, but I'm part of the way there. The part up here where I forgot this auxiliary Z2 bundle corresponds to me taking the classifying map of the trivial bundle over BZ2 on this last factor. So let me take the identity on these first few guys, and then let me fix the, yeah, that's an L. Let me fix the last factor by taking the classifying map of the trivial bundle. And I will land in a shift of K-theory, K many times. Then I use the multiplication in K-theory, and I indeed land in degree K minus L of KO. So starting from a manifold with this kind of structure, we can indeed land in a K-theory group, and indeed the K-theory group only sees the difference between these two, the numbers of twists. And I wrote it as a map of spectra partly because that's the description that I like the best, and partly because it's a little harder to say exactly what this does on manifolds. I can do an example. But it's also nice to have this description in terms of spectra because we can compute, because it allows us to compute the kernel and the co-kernel of the free to interacting map, which has this as an important component. And we get some of our results in that way. Okay, so this was one punchline I was hoping to get to. There are a few more things I could say, but I think we're at the hour, so I don't know what you usually do, if anyone needs to run, or Justin is shrugging.
We can, I mean, if people want, if they have burning questions now, they should see a doctor, but then also they could ask them now, and then we could go and do a little bit of bonus content if you want to hit some more punchlines before everyone leaves. But yeah, if people have questions now might be a good time to interrupt. I have an annoying philosophy question, which
All right,
I
let's
will
go.
save to the end, though. I think it could be, it's yeah, it'd be derailing.
Okay.
So
Okay, fair enough.
okay,
All right, thanks a lot for attending.
I'm not seeing any other questions, so we'll just move on. Yeah,
I'll ask a question.
All right.
Okay.
Just because I was driving when you gave the definition of this EL comma K. So it's there, but so L and K, I always have two Z2 symmetries, right? L and K just label the types that they are.
Yeah, I could imagine taking more, L and K don't both have to be one. I could take, so I'm not sure what you mean by it, only, they're always being two. I could take however many copies I want.
So then I just have more Z2 symmetries.
Yeah, so I think.
So this wedge L means, right?
Yes.
So I have like L many T squared equals ones and K many T squared equals minus ones or something.
Or minus 1 to the F, and I think that is right. Sometimes I mix up those two cases, but yes.
Right, one or the other.
Yeah.
Nice. So where are all of these Z2s coming from in the Bott spiral construction?
Okay, so maybe I should move on to the Bott spiral, and then that will hopefully answer your question. That sounds good. So actually, for the Bott spiral, really we're only going to care about having, we're not going to need that many L and K. One of them could be 1. So let me get to where that's coming up. All right, I really hope I'm counting correctly. So I think 5 is dimensional reduction and the Bott spiral. So Ryan, I know you're very familiar with this paper, but for the benefit of people who are maybe not, let me say what's happening. So I kind of said at the beginning that Queiroz-Khalaf-Stern were studying free and interacting theories using a dimensional reduction map. That map was something like take an SPT in dimension d plus 1 of some type, which I'm now going to label L k plus 1, and mapping it to an SPT in one dimension lower of type L comma k. And all right, so let me do this in the form of an example because I think that's a little more concrete. So, and this is an example that they present in their paper, which you can read. It's very explicit and nice. So let's consider in dimension 2, let me consider a class D prime superconductor. So what is D prime? D prime is a version, it's a modification of the Altland-Zermbauer class D. And for us, it's going to correspond, let me just write, this is going to correspond to D pin. So this 1, 1 symmetry. And let me maybe say why that is. So I'm going to be following figure 2 from Queiroz-Khalaf-Stern, where they explain how you could build a class D prime system. So I'm going to go in between the page here, but I would start with some bulk system and in 3D maybe, and then my class D system would be maybe living in 2D here. So it's a class D system, and it can have some number of it can have some number of edge modes, and so I'll pick some invariant there. The way to construct D prime is to then take another system and construct it so that it's also class D, but it's going to have the opposite chirality or the opposite invariance. What you can do is you can stack these two systems. And if you look in their paper, they draw this much better than I am doing on my iPad right now. But they stack these two systems. And normally when you stack class D systems, you could kind of cancel these invariants. But they're also going to enforce an additional symmetry R. So this symmetry R could be viewed as a spatial reflection, or it could also be viewed as a conservation of spin mod 2. And what this does is it prevents the invariance from canceling. And the other thing to observe, okay, so this prevents cancellation of these two opposite guys, but in addition, the fact they're exactly opposite means that the system also possesses a time reversal symmetry. Okay, so far I told you, yeah, so overall we have this 1, 1 that's corresponding to this time reversal symmetry that came up when I stacked the two opposite guys, and this symmetry R that's preventing me from coupling them and just kind of forgetting everything. So I have one anti-unitary time reversal symmetry and one unitary symmetry R, and that's my class D prime. Now, how do I, do dimensional reduction? Well, actually, let me say this a bit more carefully. The dimensional reduction will be looking at the edge, or going around the edge, the one-dimensional edge of this system. So concretely, I have some Hamiltonian for my D prime system. And what I'm going to do is I'm going to add on a mass term that varies in space, and I'll follow the notation of their paper. So add on some mass term, localized just to the edge of the system. And you can show that this mass term is going to break the original time reversal symmetry, and it's also going to break the reflection symmetry, but it's going to preserve a new kind of symmetry, which they're going to call T tilde, which is their product. And so this system, once you add this mass term and then you look at the edge and solve for the behavior of that system, it's going to be class BD1. So this T tilde squared is going to be 1. T tilde squared is going to be 1. And so then they notice, okay, this system on the edge looks like a Majorana chain. It looks like the time reversal symmetric Majorana chain. Okay, so that's where one of these, that was the explanation for one of these situations with L, K. And on the free side, this kind of dimensional reduction is just going to be an isomorphism. It's sort of a rearrangement of these letters. Let me start off with, where now I can just kind of use the Clifford suspension isomorphism to rewrite my system in this way. So that's an isomorphism. And then we had the question of how would we do this on the interacting side? And that also comes back to Smith homomorphisms. So I can write that down in a minute, but did I sort of address your question, Ryan, about which L and K will show up here?
So T is one of them and R is the other one, that's right?
Yes, yeah, exactly.
But then doing this diagonal breaking, that's like choosing the representation you'll use for Smith.
Yes, yeah. So that breaking, yes. Or well, at least we're breaking one of them. Let's see if you agree with the formula. I think we're saying the same thing. Yeah. So let me do
some combined sign representation, I guess.
So what we do is we sort of break one of the we do Smith on one of the factors, and then we project away another factor. And let me write down the formula to be explicit. So let me do the example of interacting side. The example of BD1 to D prime or to D pin, which is what I described there. So on spectra, it's going to be the following. So D pin was this smash product. So I twist by sigma and I twist by minus sigma. I've absorbed the minus ones for convenience. I've absorbed the normalization factors for convenience. So this is D pin, it has these two twists. What we do is we take the identity actually on the first two factors, and then we smash with the map inducing the Smith homomorphism. So this submanifold, this map that induces this map on bordism taking submanifolds. And we apply it there. So I don't change the first C2 factor, but I change the second one. And getting my suspensions correct here. And then what we do is we project away that last piece. And what we are left with is the system with pin minus, of symmetry type pin minus. So, or a suspension of empty pin minus. And let me move this over slightly. Okay, so yeah, I guess I wouldn't say we're really taking the diagonal. So for example, this D pin guy is a Z-mod 8, and it was generated by RP3 under this map, or maybe, yeah. I'll need to double check my arrows going in the correct direction, but this is the map inducing this dimensional reduction, and I land in pin minus bordism, which we saw earlier. This is also a Z-mod 8, it's generated by RP2. So on bordism, yeah, on bordism, this is what the map does. Yeah, so maybe it's how I described. It's kind of doing the Smith homomorphism on this last factor and then kind of projecting away. And let me maybe finish by inserting an actual picture from Queiroz-Khalaf-Stern of this Bott spiral, just for fun. So they noted as you go around the free classification, if you start with an integer classification, it'll always be the integers as you go around, and you kind of end up with the Bott clock. If you look instead at the interacting order, so here we had a Z-mod 8, which is Z-mod 2 cubed, that's this 8 here. If you continue to go around and then compute the interacting classification, it'll be growing with this big factor, or this increasing factor of 2 to the n in the order. So that's something we wanted to replicate. And so let me just write down our theorems, and then I will stop. So
can I still ask you a question about the example?
Yeah, for sure.
Yeah, so earlier you said that you're going to break R and T down to the product, which is why I thought you should choose Smith sigma. Smith of like an outer product of like the two sigmas.
Yeah, that's a good point. I think, well, we found that with this definition, it seemed to replicate the behavior that we wanted. But I think you're raising a good point here that maybe the diagonal is relevant here. So
it does seem to work in this example.
Yeah, it seems to us that this map definitely works, and it definitely has the right source and target, and the right sort of behavior. And I'll write down in a minute that like it is an isomorphism on the summands in these bordism groups that depend on the spin structure. So it has a lot of the nice properties that we really liked. And so we thought that is a good candidate for this map. But yeah, the point that you're bringing up now does seem like a good one to me. So we should think about that.
Okay, thanks.
Yeah, thanks for the comment. So something we're able to show using our definitions is that the overall map is a surjection from a Z on the free side to a Z mod 2 to the some power. So it'll depend on where we started. So forgive me for a little vagueness, but it'll be 4 or 5. And then we need to count how many times we applied Bott periodicity. So I'm going to write a B for that, and then an L. And so this is, let me say if you want me to be careful about the degrees, in degree n, for n equals 8b plus k minus l plus 3, then I choose the 4, and if instead I had a plus 7 in that degree, then it'll pick the plus 5. But the formula got a little complicated. So the takeaway is that we do show that it's a surjection onto this summand of this Z mod 2 to the some large power as the dimension increases. And another thing we're able to show using our definitions is what I said verbally a moment ago. So the interacting dimensional reduction map that we pose above is an isomorphism. So it's an isomorphism on bordism groups. modulo some summands that don't depend on the spin structure. So we are a little bit tentatively calling those bosonic summands. And another thing we showed was what I hinted at the beginning when I started drawing this diagram, that we do have a commutative diagram. So the free to interacting map and this dimensional reduction map do commute, which seems like a useful thing to know. Okay, so I'll stop there. Thanks a lot for listening and for offering comments and questions.
Good. So maybe, yeah, thanks for the talk, Cameron. Maybe I'll ask the first question. So why does that map that you define deserve to be called free interacting? Like, is this just based off empirical evidence, such as the one you have listed here, which are very convincing, or do you have even perhaps more conceptual argument?
Well, I think what a free to interacting map should do is have the same symmetry type of the system. So the symmetry type we had on the free side for the spot spiral was this Clifford L, K symmetry. So I think it's well justified to have a free to interacting map that encodes that symmetry on the interacting side. And so I didn't, as you know, I didn't give the full definition of the free to interacting map. I just told you the Atiyah-Bott-Shapiro component. But to me, that map is convincing because it's really using the data of the twists. So for me, conceptually, these maps are due to Fried and Hopkins, and the fact that they really use the twist, the data of the twist. So here we're twisting by sigma. We really use that by taking the Smith homomorphism. We really needed to know that data when we were doing this map. We didn't just construct some random spin manifold from a pin plus manifold we plugged in. We really used the data of the twist. And so for me, I feel that we are using all of that data that we input by using the Smith homomorphism here and using this K-theory class here, and we do land in the right place. So I think we're using all of the information that comes from us from the tangential structure to produce a K-theory class. So that's one reason I like this ABS L, K map. And then physically, like, it's good that the computation worked out to replicate the behavior we wanted to model. So I'm not sure if there's another conceptual checkpoint we should hit there that you had in mind.
So maybe, by the way, to phrase my question, is that, does this generalize to other symmetry types?
Yeah, I think as we've discussed, you could definitely pose a very similar map here for certain other twists by your group. And I think it's work in progress to see if that replicates the behavior we want, what behavior we want physically. There's something a little special about these Z2 twists that we're considering. So the special thing being that the fermionic group algebra of these Z2 twists really gives us a Clifford algebra, and that K-theory is built out of Clifford algebras, and we have the suspension isomorphism. If you have a general fermionic group, this classification, let's see, where did I write it? Yeah, so if you have a general fermionic group and the symmetry is like some symmetry G here instead of Clifford L, K, I'm not necessarily going to land in an untwisted K-theory group. I'm going to land, forgive me for maybe getting the shifts wrong, but I'm going to land in some equivariant K-theory group. And then there's a bit of a question of how we deal with that equivariance on the free versus the interacting side. So parts of the story will generalize, but then parts of the story will get a little more complicated when our symmetry isn't of this nice Z2 form. So that's what I would say.
Yeah, that's great. Thank you.
Okay, thanks. Maybe I should stop scrolling. I don't know if that's very annoying to the viewer.
Other questions or comments?
Cameron, I had a question. I think you mentioned this in your summary, but did you say this free to interacting map is surjective?
So it's a surjective onto some z mod 2 to the n for some large n. It's not necessarily surjective. Overall, there could be other summands in this interacting classification. What we're seeing is and those bordism groups are difficult to compute in all dimensions. Like that's pretty hard. So we were satisfied with looking at what Queiroz-Khalaf and Stern are really modeling. And in their paper, they're sort of looking at the class of like this minimal Dirac Hamiltonian that they could write down, and they asked sort of what's the interacting classification from that model. But there could be more things that are happening. But we do see that it's a surjection onto this summand that we wanted to study.
I see. Okay. Yeah, I'm curious what happens with these examples that people have come up with of like intrinsically interacting fermionic SPTs. I wonder like what happens to the how does the map interact with that that result?
When you say intrinsically interacting, you mean phases, so interacting SPT or like invertible phases that don't come from a free theory or have no free analog?
Yeah, exactly. Exactly.
Yeah, that's also a super interesting question. That's not the one we were studying for the purpose of this application, but it is definitely something we're interested in. That's when this free to interacting map has some interesting co-kernel.
Right.
Yeah.
Nice. Cool. Thanks.
Yeah, thanks.
Okay. Well, Leon kind of scooped my question in part. So in part, I would not have said it so sophisticated, but hearing and seeing no further questions, I guess I'll stop the recording, and thanks everyone for coming. Thanks again for the talk, Cam.
Thanks.